Today we have a presenter who is uh, Mr. Vijay Prakash Dwivedi. He has been working as a PhD student in NTU, and his supervisor is Professor Javier, and he has been working in the area of so-called graph neural network. So before we start the presentation, I'd like to share a little bit about our SLS talk. SLS talk basically is a platform where we share our research work. I'm also a PhD student working under the supervision of Professor Francis Lee and in the area of reinforcement learning. So basically we do research, we publish our work, but then it doesn't reach out to all the audiences out here, even in within NTU. So it is a very good platform where someone can share the work, and it helps to increase your citation, paper citations, and there are so many other benefits presenting your work in this platform. So I'd like to share two things basically here. So what we do is basically whenever we have this kind of presentation, we record that video and then we upload that video in our YouTube channel. SCSE-GSC Graduate Students Club has its own YouTube channel. So I'll show you, and I'll also send you the link. Here it is. So if you go and you go into YouTube, and if you search NTU SCSE-GSC, you will find this link. I will also share this link to you. And then we have already uploaded these two videos, the past events, and you can see there are so many views, already more than 130 views in each video over here. So you can also visit YouTube channel and see and watch the past events. And moreover, I want to also share one more information with you. If you are interested in giving a lecture in SLS platform, let me welcome you as well. And then I will share a form. There is one, oops, sorry, let me share a screen over here. So this is the YouTube channel. I will share the link. And this is the form where you can fill some certain information, and we'll definitely contact you later for the SLS presentation. I will share the link of this form as well. So what you have to do, if you are interested in presenting your work, what you can do is you fill up the form, and we will definitely contact you for further procedures. So please do keep in mind these two things. I'll share all the links in our chat. So without further delay, let me welcome you all, and especially the presenter, today's presenter, Mr. Vijay Prakash Dwivedi. His talk will be related to a kind of transformer, generalizing the transformer in regards to a graph neural network. Vijay, are you there?
Yes, hi. Hi, Manoj. Thank you very much.
Yeah, now you can share your slides and you can start your presentations.
Okay.
Okay. Yeah, we can see that. Yes, Vijay, we can see your slide.
Okay. Yeah. So I'll start now.
Sure, sure.
So, good morning, everyone. My name is Vijay Prakash Dwivedi, and I am a second-year PhD student in the School of Computer Science and Engineering at NTU. My supervisor is Professor Xavier Bresson, and I'll be presenting this work with him, which is titled "A Generalization of Transformer Networks to Graphs," which is a recent work. And before starting, first of all, I would like to thank the SCSE Graduate Students Club for hosting this wonderful student lecture series where students inside NTU can present the research and have exchange with other students. And I would like to thank Manoj and Abby for giving me this opportunity to present my own research. Thank you very much. So I'll start now. So first of all, I would like to give some idea of what the title of this talk means. So there are two keywords to note: transformer and graphs. Transformers is the go-to neural network architecture in natural language processing. It works so well on language modeling and several other language processing related tasks across languages. And graph neural networks are the state-of-the-art deep learning models for performances or for learning on graphs, structured data sets, or in domains where data sets can be represented in the form of graphs. So we try to look these two things, and the difference between these two is in NLP, we have data sets mostly which are sequential structures. So they're sequences of sentences. In graphs, uh, there are domains which can contain graph structure data sets in arbitrary structure. They can be different structure in different graphs. So this is the difference between these two fields and the data sets that is encountered in these two fields. So we try to, since transformer networks are very successful recently for NLP, we try to generalize that not only for sequential structure, but generalize to data sets of arbitrary structure so that they can handle graph data sets and can be applied to a wide range of domains. So as a result, we present graph transformer. So this is the idea of the talk today. The outline of the presentation is like this. First, I will introduce the background and motivation by connecting the two fields of NLP and graph representation learning, and like finding ways how we can extend principles from one field to another. Then I'll highlight the objective of my work. I'll have a detailed discussion then on the key design aspects which leads towards the generalization of the transformer on graphs, which are graph sparsity and positional encodings. It will be followed by the detailed description of the building blocks of the proposed architecture. Finally, I'll conclude with numerical experiments, highlighting the key results and the main takeaway messages. So I will start with the background and motivation. So I will connect these two fields, NLP and graph representation learning. First is the NLP. So in NLP, before transformers, RNNs used to be the state of the art for most of the learning tasks on concerned with languages. So in 2017, transformers were developed by this paper from Vaswani and his co-authors in 2017, and uh, since then it brought a huge shift in the way how languages are learned with deep learning. So at the core of transformer is the multi-head attention mechanism, which is represented by this formula. In this, each word attends to all other words in a sentence, represented by this, and combines the information, received information, to generate the abstract representation for the word at the next layer. So uh, it lets go of the sequential processing which was inherent in RNNs, and it also allowed to overcome the bottleneck of RNN-based architectures, hence bringing a shift in uh, how deep learning models are trained on languages. And the figure here shows like for every word, so here it's only shown for transformer. So for every word, the feature representation is generated by combining or by attending to all other words in the sentences. So it has become transformer based architectures has become a universal building block in deep learning, and the models which are based on this multi-head attention mechanism are state of the art in language modeling and so much NLP applications. It led to subsequent work such as BERT, GPT, and GPT-3, and several other works. And there has been recently very powerful models with applications in almost every domains or every areas concerned with languages and text. So it has led to this, I mean, a huge impact in NLP related applications. The second field is graph representation learning. So there are several domains in real world domains where data sets are not very regularly structured. They can be represented as graphs which have irregular and arbitrary structure. For instance, in chemistry, uh, molecules can be represented as graphs, whereas where the nodes can be atoms and the edges can represent the chemical bonds among the nodes. And chemical properties can be predicted using on these molecular graphs. In physics, the interactions among particles can be represented as graphs, and in chemistry and physics, like if we are to apply graph representation learning, the good models from GRL, it helps accelerate the research in the respective fields. Similarly, in social networks, there is an abundance of graphs across commercial domains, and like if you consider any social network where users are there, so there are a lot of graphs which are there in social networks. Similarly, in medicine, neuroscience, and fields like combinatorial optimization. So to show this, like there are numerous examples of graph datasets, and hence there is an incentive to work in this area, because the applicability of the models to be developed in this field is huge. And nowadays, graph neural networks are the most successful and kind of state of the art in several of the fields where graph datasets are found. Briefly, to say what graph neural network is, it is a neural network model which takes in a graph with node and optionally edge features and builds their abstract representations of the nodes and edges by taking the explicit connectivity structure into account. So if you look at this end-to-end diagram, this is the part where GNN layer are stacked. So at each layer, the arbitrary structure which is available previously, I mean in the dataset, is considered at every layer. It's fused, and it helps to capture the that information and into the node and edge representations that is generated at every layer. Finally, the representations are passed to downstream MLP uh, networks to predict properties on the nodes, on the edges, or on the graphs as a whole. So so this is simply a basic idea of what a graph neural network is. So we try to combine these two fields, the transformers from NLP and the graph neural networks from graph representation learning, so as to help generalize transformers to graph neural networks, to graph-based data sets, and uh, we extend principles from one field to another. So objective is, as already noted, that our objective is to have a graph transformer architecture, and we approach it by looking at what led to the success of transformers, what are the key characteristics, and how can we extend or generalize those on arbitrary graphs. So the first obvious idea to do this is to restrict the attention of transformer only to the local neighbors. So this is well known and has been done since models like graph attention networks and several subsequent papers or models that have been developed on based on GATs. So in transformer, there's full attention, meaning each word attends to each other word in the sentence or the sequence. Whereas if we consider local, I mean restriction of attention to local neighborhood, for instance, if we want to generate the feature of this node, we can only let this node attend to the three nodes that it is connected to and not attend to the nodes that are disconnected from it. So this is a very well-known idea, and it has been done in graph attention networks and several other subsequent works, right? So we ask that, I mean, is this enough for the generalization? Although it's a very necessary characteristic, we find that there is another aspect to consider. So I will discuss on the two aspects. And before that, let me highlight some of the recent works in the literature. So since these two fields are very intense area of research nowadays, there has been some recent attempts to develop graph transformer, and uh, there has been some attempts to whether some local attention is useful or not, or what kind of candidate positional embeddings should be generated. But there also has been some transformer models developed for specialized cases such as temporal graphs, heterogeneous graphs, generative modeling, etc. Despite these efforts, there are some open questions whether local attention or full attention, which one is good for like better performance, whether sparse structure is necessary to have at every layer in the computational or as a computational graph, what positional encoding candidates to select, because in transformer there are positional encodings which I'll discuss later, and it's very important to consider because it helps encode certain information from the dataset into the models, and the issues of scalability and pre-training. So there are these open questions in the literature, and we try to address some of them and most of them with this work. So now the two key design aspects, graph sparsity and positional encoding. So the first is graph sparsity. I'll try to present this from the context of both NLP and from the context of graph, so that it makes so that we can be distinctive in the separation of like how it should be applied to each of the different domains. So in NLP transformers, we have full attention, and this choice can be justified for two reasons. First, uh, if we have sentences, it's most often that there is no any meaningful sparse connections between the words. For example, we don't know whether this and is there is a relation, or there is a dependency between these two words, or if there is a dependency between the two words, for example this and transformer. So we don't know which one is related to which, and it can differ as I mean it can vary with context. So for instance, for certain domain or certain context, a word depends on certain other word, it may not apply universally to all other contexts, right? So it's there's an absence of sparse connectivity structure among the words in a sentence. So it makes sense to use full attention and let the model learn or decide how the words depend on each others. The second reason is that in NLP, because the sequences or the sentences are often less than tens or hundreds of words, it makes it for computational feasibility. So it is computationally feasible in memory to have full attention and let the model find the word dependencies in the form of attention scores. So for these two reasons, it can be justified that, okay, NLP transformers can carry out full attention, and it has been proved to be very beneficial, like given the work that has been done as follow-ups. But in graphs, there always some connectivity structure present. In if you see graphs arising from several of the domains, the connectivity structure that is there, it presents a rich source of information that we would not want to miss when we are trying to learn a model for a certain task. So first is that the structure we want to use, and the second is that if we were to do full attention on graphs, it may not be feasible for a lot of data sets. For example, there can be graphs which have thousands or millions or billions of nodes. If there are hundreds or thousands of nodes and we were to do full attention, it although it would be feasible on memory, it would take a lot of time as compared to the sparse attention. But actually, there are in real world there are a lot of cases where graphs have millions of billions of nodes, so it's not feasible. It gives out of memory error on machines even which are like very high memory. So for reason, because graphs have sparse structure which we want to use and full attention is not feasible, we it makes sense to go by using graph sparsity and have attention restricted to the local neighborhood. Now this idea is well known, and this idea is core at the core of GNNs, because they consider feature aggregation using the local structure, and it has been proved that it's a good inductive bias for generalization. So the way full attention or sparse attention for the domains of NLP or the domains of graph. So this kind of hints that, okay, we should maybe full attention is not the way to go while generalizing transformers on graphs, and hence we proceed with attention restricted to local neighborhood. The second key aspect is positional encoding. So the multi-head attention mechanism of transformers are invariant to the ordering of the nodes. So it means that a transformer considers the sentence as a multi-set of words rather than the sequence itself. So a multi-set of words means the multi-head attention mechanism does not have any notion of uh, the ordering of the words in the multi-set, right? So we would want to encode this information about the sequence or about the ordering of the nodes in the transformer, and that is done by using some kind of positional encoding. So in Vaswani and his co-author's paper, the original transformer, the positional encodings are represented by sinusoidal uh, positional encodings, and it is added at the input words in the original transformer. So this helps the model know, or it helps encoding of the underlying sequential information of the words in the sentence. So this is a very critical aspect behind the success of transformers, and we look towards extending this as well when we do graph transformer. And recently there has been some research, if you look at references 1, 2 and 3, there has been some research which tells that if we are to improve graph neural networks in general, the integration of positional encodings is critical and it improves performances. Overall, it helps overcome the failure cases of GNNs. For example, it was shown that GNNs may fail to distinguish two non-isomorphic graphs or fail to detect cycles in graphs. So if GNNs are to succeed in these very fundamental tasks in graph theory, positional information is critical. It was shown in the research, right? So it also motivates that if we are to go develop graph transformer, we must look at this positional encoding aspect, and we use Laplacian eigenvectors uh, as positional encodings in graph transformer. It is adapted from a recent work of ours in which we use Laplacian eigenvectors as positional encoding. And uh, if we try to relate that with the original transformer, the sinusoidal positional encoding of the original transformer, the Laplacian PE, it represents a natural generalization of the sinusoidal PE used in NLP transformers, because uh, in the NLP transformers, the positional encodings can be interpreted as the eigenvectors of the line graph, which is the sentence. And in the graph, we are taking the Laplacian eigenvectors, I mean, of the graph itself. So, I mean, the eigenvectors of the Laplacian of the graph. So it's a very natural generalization and extension of it. So the positional encoding and the earlier discussed graph sparsity. These are the two key aspects we consider while designing the architecture. Now I'll describe the uh, architecture in detail, and I'll discuss how it's different, or how it's generalized from the original transformer architecture, so that it can be easy to refer to different components and easy to follow. So this is the original transformer encoder from Vaswani and co-authors from 2017. It has the important blocks such as input added with positional encodings, the multi-head attention mechanism, and the feed-forward module. So on the right, this diagram and the right diagram, these two are the architectures that we propose, with the arrows pointing to the key design alignments. For instance, the same way we add the positional encodings at the first layer before the input. I mean, before the inputs are passed to the graph transformer layer, and we restrict multi-attention mechanism so that it only considers the neighborhoods represented by the J here, and we have the feed-forward module similar to what was there in the original transformer. So now I'll discuss the characteristics and how it's different from the components of the original transformer of Vaswani and his co-authors. So the first difference is that, as already discussed several times in the talk, the attention mechanism is the function of neighborhood connectivity. So for each node I, it only attends to the neighborhood set, the local neighborhood set J. So if you recall the formula for the the standard transformer mechanism, transformers attention mechanism, there was an S here, which denoted every word in a sentence. But here we have NI, which denotes the node neighborhood. So the formula is more or less the same, but only the neighborhood nodes are aggregated while doing feature aggregation at every layer. So this is the first difference. The second difference is the positional encoding. We use k smallest non-trivial eigenvectors of a node as the positional encoding, following a previous research work of ours. Uh, the third is we replace the layer norm by a batch norm layer. So in the original transformer, in the module here, the add and norm, they used layer norm and they got better performances by that. But in graphs, we may have like batches of graphs which have variable sizes. For instance, we may have graphs of, let's say, 10 nodes or 15 nodes. So it's very irregular in the number of nodes that we encounter. So we found that experimentally, batch normalization layer, if we replace the layer norm with batch norm, it gives better performance. So we use batch norm in the feed forward module. And finally, at the right, if you see, there are two feed forward heads, and there are actually two pipelines, symmetric pipelines, one for the nodes, one for the edges. So this is the architecture which we extend so such that we can have explicit edge representation at every layer, and it allows for encoding of available edge information of the graphs in the graph transformer model. So to detail this, for instance, if consider graphs of molecules where on the edges there can be some bond information represented by Eij for the bond, I mean for the edge ij. Similarly, in knowledge graphs, for example, the edges can represent or can have information on the relationship type. So what kind of relationship or what kind of property the relationship has. So this is also a information which we want to use. So what we do is we use this Eij information to improve the implicit attention scores and then use the resultant scores in the aggregation during the aggregation equation. At the same time, we pass this to the edge feature pipeline. So in the schematic diagram here, the edge is used in the attention scores as well as the resultant features are passed so that we have a node and edge feature pipelines at every layer. So this is an architecture which is ideal for data sets where there are some edge features we want to include or maybe some edge properties we want to predict. So this is the architecture for the graph transformer with edge features. So that was about the architecture. Now I'll show like how graph transformer that we propose fares on benchmark data sets. So we evaluate graph transformer on data sets of zinc, cluster, and pattern, which is from a recent benchmark, and we compare with the similar budget of 500K parameters of all the models, and we see that GCN and GAT, which are very powerful but baseline GNN models, graph transformer obtains competitive performance and beats both of the baseline GNN models. Another thing to note is that there's a significant margin of performance gain of graph transformer as compared to graph attention. In zinc, the lower scores are better. In cluster and pattern, the higher scores are better. So in all the three, there's a difference between the performance, and graph transformer is better than the baseline two models. It also says that, for example, graph attention had this graph sparsity, but it doesn't have the notion of positional encoding. So it may be failing at several fundamental properties in graph theory that we as a model would want to be successful on. So there's a very clear significant gain of graph transformer as compared to graph attention. And hence its graph attention networks has been used for a couple of years as a attention based GNN baseline. So graph transformer as opposed to graph attention network emerges as a fresh and powerful attention based GNN baseline. Now, if you compare with the state of the art performance on these three data sets, the gated GCN model is the best, and actually graph transformer is unable to beat that. So overall, it achieves competitive performance, but gated GCN, which is a GNN model, is still the best. So we kind of look this as this work was only a straightforward generalization of transformers. So we have a very basic graph transformer model. We did not attempt towards achieving state of the art on these datasets, but rather to have a straightforward generalization model which can be extended, and ultimately domain-based inductive biases are critical to have state of the art performances on the datasets. So this work, it proposes a very straightforward general graph transformer, and in future we would like to improve this, trying to understand the successes of several subsequent works of transformers. So now, during the end, I would like to give some takeaway message in the sense that we try to address some open questions that I highlighted earlier during the start of the talk. So if you recall the open questions, there were some uh, differences in the literature, like whether local attention is good or not, whether the sparse structure should be considered at every layer of the graph transformer, or the questions on positional encoding candidates. So if we see, we performed an evaluation of using the restricted attention to local neighbors and the full attention. So in all the data sets at every instances, if we had sparse graph structure during the computation, it always gave the best performance, and there is a significant margin. There's a very big margin. So if there is a graph data set, its information, there's a lot of rich information along the sparse structure that we want to encode directly at the layers. So it helps, the first thing. So it tells that local attention and sparse structure is important. Also, if you see the computation times, for example, if you see the epoch seconds here, it's also very efficient, because obviously, I mean, it's obvious that if we are to do full attention, it will have a big complexity, time complexity. So this is the first result that we got, and we try to address this question. The second, so yeah, the message is that attention to local neighbors is critical. The second question that we address is in the positional encoding. So what kind of positional encoding candidate is necessary? So recently there was a work called GraphBERT in 2020, which used some kind of Weisfeller-Lehmann positional encoding. It is represented by WLPE. So when we use WLPE and compared with Laplacian PE that we proposed, Laplacian PE gave better performance. And it also says that Laplacian PE is a very ideal candidate for PE because it has certain good properties that we want. For example, it has this distance away information. For example, uh, nearby nodes have similar features and distant features nodes have dissimilar features. So this kind of distance away property is there with Laplacian positional encoding, as well as they're unique for every node. So each node can be uniquely distinguished. So because of these reasons, Laplacian PE is always the better as compared to the WLPE. And with WLPE, it leads to overfitting. For example, if WLPE is applied as opposed to no PE, it increases the training accuracy, but it decreases the performance. So it leads to overfitting, the WLPE. So the message is that Laplacian PE is a well-placed positional encoding candidate at the moment for graph transformers. Now, if you look at this figure, remember I discussed two key aspects, the graph sparsity and the Laplacian positional encoding. So if you look at this red highlighted and the bold, black colored bold scores, they are obtained at the rows where there is Laplacian positional encoding and at the column where there is sparse graph. Hence, it validates that sparse graph and Laplacian positional encoding provides the best performance, confirming that these two are the key design components that we should consider when doing graph transformer. So, so as a result, we have this architecture in front of you, and I'll conclude the talk now. For more details, you can refer to the paper or try the implementation in the open source GitHub code. Thank you very much.
Vijay, thank you so much. Thanks a lot for this wonderful talk. And uh, yeah, and this graph neural network seems pretty interesting. And I think the transformer that you are proposing might be very helpful in machine translation as well, I guess, and the NLP, basically in the field of NLP. Am I right?
Yeah, if we are to consider some sparse structure in NLP, if there is some source of that, it can be useful there as well. So it's very generic, and we hope that it could be applied to a lot of fields in future, and we ourselves will be doing some extensions on the work.
Right. So so then quickly we can receive queries from our audience as well, right?
Okay,
So
sure.
so friends, may I request you can just unmute yourself and then please do uh, forward your queries right away here. Let's wait for the queries. Anyone? Please do
Okay.
unmute
Hello.
yourself. Yes, we
Hello,
have.
Vijay.
Yes, who is this?
Yeah.
I'm Chung-Soo. Thank
Oh,
you for
hi.
the presentation. Yeah,
Yeah,
hi.
yeah.
So
Hi, Changshu.
just one simple question is that can we say that just the sequential data or time series, can we also consider that, I mean, look at that as a graph data which has something like a very special structure like one-way direction, something like that?
Yeah, it is like that. So for example, in the standard transformers, although has this full attention where a node attends to each other node in the sentence, the sequential information is passed as the positional encoding, right? Because the sinusoidal positional encoding, which is added to the input in the original transformer, it represents the underlying sequential connectivity, and that can be interpreted as the eigenvectors of the line graph. So I mean, it could be tried like how if we were to just consider each word has like two neighbors previous word or the next word, and see, like, we could try that as the like as using the graph transformer, but overall, like, even standard transformer considered that sequential information using positional encodings.
So can we say then, like, if we like try to use the sparse connection, even in those normal transformer, would it make quite big difference?
I haven't experimented that myself, but hence I don't know like what would be the result, but we can do that. It will be a very interesting experiment.
Oh, okay. Thank you. Thank you.
Yeah, thank you, Changshu.
Thank you, Changshu. Let's we can have still one more query. Is there anyone friend out there?
Hello.
Hello.
Hi, Vijay. It's a very interesting topic.
Okay.
Both of the domain are very new to me, like
Oh,
graph networks and NLP. But something interesting I found that the graph networks, is able to represent several domains, starting from neuroscience and the other aspects as well.
Yes.
I'm actually wondering if this whole talk is based on NLP, right? Using the transformers. Is there any way we can use this graph and the transformers for neuroscience, like kind of like the human brain neuron modeling? Is there any way we can do that?
Yeah.
Because I wanted to set the context, because in the neuroscience, human brain, the neighboring neurons, or it actually happens in a sequence. The earlier neuron fires, then the next neuron fires. There is actually a temporal sequence. So the time is actually an additional component in those kind of neuroscience, or those kind of field. I was wondering if we can, add extra element, extra parameter for time. Is there any way we can do that in using any of your work?
Yeah, so I mean, the transformer, graph transformer that we present, it inherits from, or it inherits some principles from the NLP, in the way that how transformers were first developed for sentences and for machine translation. But it's a very general deep learning building block in today's world. So recently, like even in speech, in on vision, computer vision, the same model is being applied. So in neuroscience, there are some data sets like human connectome. There's a project called human connectome project. It represents some connectivity structure among regions of the brain. So it provides a data sets like graphs in the field of neuroscience and certain applications. So any of the graph networks and even the graph transformer can be applied there, and like the temporal information or the structure can be very arbitrary. So that arbitrary structure can be used with any of the models like graph transformer or any of the graph networks in general. And I think there is some work ongoing in this direction, where like if you want to do a temporal kind of thing, there's a sequential GCN. There's some work in this direction, sequential GCN, where there's for every sequence there is some graph transformer, because it's in such case where there is a temporal sequence, but at every sequence there is a big structure that we want to learn. So uh, the same structure, the same architecture, graph transform can be applied, yes, to neuroscience. And there are data sets, as far as I know, like there's a connectome data set, which uh, is ideally the thing you're looking forward to.
All right, sure. Thank you.
Yeah,
And
thank you.
another follow-up question for this is like, what are the limitations for this kind of graph transforms, or like where we cannot apply this kind of models?
So I mean, there's a very broad question. So first, like, yeah. So
I mean, with the current
So
structure,
anyways,
what is the
yeah,
limitation you have?
just trying to present just a projection towards that, towards the answer to this question is like, it's very early in this field. Like, although we say graph deep learning, if we have like some depth of models, we don't see, or we don't understand like what is the performance gain, or in several instances, if there are deep models deep layers of GNN stacked, it doesn't result in gain of performance. In some cases, there's a decrement of performance as well. So it's not clear like how to stack or why we need to stack multiple GNN layers. That's the first thing we don't know. And then the second thing is like whether that local feature aggregation is important or not. So there's a case of homophily and heterophily in graphs. So homophily is when nearby nodes contribute to the feature, and heterophily means nearby nodes do not contribute to the feature, right? So if we are doing some local aggregation, there's an underlying assumption behind it that maybe nearby nodes are important for feature representation of a central node, right? So there is this assumption, but recently, if right in 2021, there's some work which tries to differentiate these two aspects, and yeah, so there are a lot of limitations which are there with this module as a whole, the graph neural network. But it has shown some initial success on several domains, hence it's widely I mean it has become an intense area of research. And to your question, like yeah, this is a very broad question, and a lot of questions, the answer to questions we don't know in this particular field.
I think you answered well for this question. I think that.
Yeah.
Anyway, thank you, Vijay, for your
Thank you, Avi.
wonderful presentation. Thank you.
Thank you.
Yeah, Avi, thank you so much for the questions, and Vijay, thank you so much for this wonderful talk. And let me inform you, you can once
Can we
your
take some more questions if anyone has? Yeah.
yeah, you surely, sure.
Yeah. So if anyone
If
has
there's
any
anyone,
discussion question, we could discuss, and
yeah,
then if not, we could conclude.
yeah,
I think we still have 10 more minutes, right? So we can still accommodate a few more questions.
yeah.
If they can use the chat box also if they want to type out the questions.
Yeah, and moreover, I think we're going to upload this video as well in our YouTube channel, and they can, even contact Vijay. I think you can find his email address in his website as well.
Yeah.
Yeah, right over there. Uh, yeah, I think we can conclude this session. And let me inform you, Vijay. Once your supervisor approves your video, you can uh, claim 2 hours GAP,
Okay.
gap of
Yeah.
two
Sure.
hours. So
Thank you.
please do that one, and let me know if you face any problem regarding claiming this GAP of 2 hours. And I also encourage all my friends out there to consider presenting your work in this platform, because it's not only about gap hours. It's all about collaborating with each other as well. Like for example, this video will definitely let you know a little bit about yes, transformer, a little bit about graph neural network. And if you are interested in that field, or if you need any kind of information regarding that one, maybe you can contact Vijay, and and start a new project, collaborating with each other. So thanks a lot. And let me stop this recording. And thank you everyone for joining this